Hello guys, this is Leonardo Cap, and in this video today I'm going to talk about the BAO analysis. I'm going to first of all let you know where you can find the recent BAO data. This data set is containing or obtained from the SDSS experiment and as well as the dark energy survey result. So there are two different data sets for the BAO, and they have been doing these experiments for nearly 20 years. DESI is more recent, and SDSS is accumulated for 20 years. So we have at most 8 data sets over here, and it has DESI data sets, and the Z is nearly about 0.1 to 2.8, I guess. So we will see about it. Now, since BAO analysis is a little bit tricky, so many of you have asked that, okay, where we can get your BAO analysis code. So in this video, I'm going to tell you everything about the BAO analysis, where we can find the code, and as well as what are the things, how we can code it to actually fit our model parameters in Python. And again, I'm going to talk about, you must have, amazing speed. Secondly, many people have asked that, let us say I have different data sets. For an example, I have various data sets. Consider you have BAO. BAO had two data sets, BAO SDSS and BAO DESI. Now you have Pantheon data sets. Let us say you have Pantheon samples which contain nearly 1701 data points. And other one is, let us say, Hubble data sets, which we can call it as a CC data set, Cosmic Chronometer data sets, which is nearly containing 31 data sets, right? Now, supernova data sets can be found as Union 2.1 or maybe some data sets called also dark energy survey supernova data sets, right? And also we have these SUS calibrated data sets, which includes in the Pantheon, right? So now when we have different data sets, therefore they have different observables. For an example, if you are considering BAO data sets, then there is an observable called RT, which is called the sound horizon distance. All right. So I am not explaining what is basically BAO and what is sound horizon, although I will give you every mathematical part that is that is important, but I'm not going to say what is the physical implication, otherwise the video would be too much long. So RT, that is we have to calculate. This is kind of again called a standard ruler, and this after the Big Bang, there we already know we have the cosmic microwave background. So as long as universe was not dominated with its expansion, there was a contraction and expansion of the radiation fluid. And once the expansion of the universe dominates over the gravitational well, we can say that the oscillation stopped, and the signature, one can say that a signature of that oscillation, the radiation can contract and expand. It has been imprinted on the cosmic microwave background dataset. So RT is kind of again a fixed type of constant, although you require some model to obtain it, otherwise you cannot obtain it. All right, but you can see it there. So there are different ways we can find out this RT. People are trying to measure, because these RTs can be found in terms of galaxy evolution and so forth, structure formation, galaxy evolution, and from those different analysis, galaxy analysis, people try to find out that what would be the because this is signifying the distance, so what would be the distance of this sound epoch. Now RT is for the sound horizon distance, or you can say that the drag sound horizon distance. All right, drag, why? Because if this length is stopped at some point, and since the universe is expanding, so it gets stretched, therefore it has effect of dragging. Now this much I am going to tell you. So first of all, I'm going to tell you the sources where you can obtain the BAO analysis. So in here, first I'm going to show you that where we can find the BAO data. So this is the paper corresponding to SDSS survey of BAO. BAO stands for Baryonic Oscillations survey. All right. So now if you will see, this has been published in 2020, sorry, it is published in 19, but they have recently updated in 9th July 2024. And if you will look at the page number, table 3, then you will see, we will find something interesting over here. Let me just show you. Over here, they have given a table and they have given that what are the traces or how many number of points they have used. So at this redshift, how many galaxies or whatever the end traces are there. So these are from these samples they have extracted the Z effective and they have extracted some observables over here. So now I'm going to talk about only BAO data. I'm not going to talk about the RSD as well as BAO plus RSD datasets. All right. So basically, because RSD datasets containing your F sigma 8, which can only be computed after you will do the perturbations. So right now I don't want to talk about the perturbations. I am only focused with the background analysis that you can do. So what we are requiring is the Z. So this is the Z that you have required. Z means the redshift. So you have the redshift data point 0.15, 0.38, 0.15 up to 2.33. Now you have two duplicate data sets, so there is no problem. So we are having 2.33 and 2.33, and corresponding to it, you have some data sets. Now if you will look at it, you can see over here that at 0.15, you have only dV over RD. So what is dV over RD? I'm going to tell you. But these are the observable quantity. RD, that is you can observe. But here you cannot simply observe the RD. You have to, if you want to apply a constraint, you have to obtain this whole quantity, as they have obtained this whole quantity, and you have to also calculate from your model what would be the dV for RD, and afterwards then you can calculate RD. First of all, I'm going to tell you that RD depends on various quantities. Now, since we are talking about the very early epoch of the universe, then RD is basically depending on what would be the geometry of the universe, as well as what are the components that is present there. Now, since we are building our model and we are basically focusing on the late time epoch of the universe, so here we cannot simply obtain the RD information from the early time. So what we have to do is that we have the model and we can treat RD as a free parameter. So RD has some kind of integral form, but we can say that now I have the present epoch datasets, late time epoch datasets, and let's treat RD as a free parameter and let's see that how it is matching. I told you that this RD is basically kind of standard ruler in the universe, right? So therefore this RD must not change. All right, but again, these cosmological data have different way of obtaining these data sets, and obviously this whole cosmology is changing day by day. So whatever the data that we are obtaining, it contains a lot of errors. So therefore, that when you are going to do different data sets, you will probably realize that you have some different result when you are going to measure this one. But that is not a problem right now. And statistically, this variation should not be very high. If it is very high, then either your model is not good, or maybe something is problem with, maybe it requires some new physics. All right, so considering that whatever the data that we have is perfect, is good, and statistically significant, so what are the observables? The observables that we have is dV over RD, dm over RD, and dH over RD. Now you can see that for certain redshift we don't have these data sets and these data sets. All right, so the data sets, what we are considering is that it must require something with plus and minus and so on. So it must contain this plus and minus. So if I will show you some data sets where you will have something over here and over here. They have been obtained by considering some basic model, but again we are not going to take those data. So first of all, something has to be clear, that for certain redshift we are not having these quantities, then we have to rely on this one and this one, right? So here you can see that you have different observable dV over RD. Afterwards, the redshift, in remaining redshift you have dm over RD as well as dH over RD. right? Now dm over rd is again again you can obtain. Let me just tell you, I will show you in a moment. So now you can see that when you are going to calculate the chi-square, you have to calculate the chi-square corresponding to this data set plus this data set and plus this data set. So I also thought that, okay, we can, just only consider either of these two, because you can see that uh, beside this redshift, you can have these data sets for both the, we can have the data sets for both these observables. So we can just, calculate these things. But again, I told you that statistically it is significant. That's why we are going to, calculate the chi-square by considering each and all these quantities. So chi-square bao, I can say that chi-square bao is corresponding to this data plus this data plus this data. So I hope this is clear. All right. Now moving to another data sets which we call the DESI data sets, dark energy survey. And from this people have obtained the 7 data sets, and here it's, you can find it because they have submitted to JCAP, and I think probably it is now in the peer review, or maybe it has already published. All right. So now if you will look at the table 1, you can see again they have their tracers and in which redshift they are basically tracking these objects. And from here they have obtained the J effective, and this J effective is starting from 0.295 and up to 2.330. Again they have the same structure, that for this lower redshift they are measuring dV over RT. All right, 7.93 plus minus 0.9, and for redshift 1.491, again you don't have this dm over rd, dh over rd, you have just only dv over rd. So again in this data sets you have dv over rd, dm over rd, and dh over rd. And considering that we are not working with the Planck data set, so I have to treat rd as a free parameter, right? So these are the data that have been obtained. Now I have to assume a model, I have to construct a model, and then I have to, again, using our parameterization technique, we have to calculate this dv over rd, and we have to make a difference. And then the way we are basically calculating chi-square is the data minus the model that is going to produce at certain redshift over the sigma I, and then we are going to take a squared. So here what is sigma? Sigma is basically this plus and minus. So you do not, because this data set is containing not a very vast amount of error, the error bar is not very large, so you do not require any covariance matrix. So for each data sets you can just simply calculate the sigma I, and then you can square it, you will get the chi-square for any data sets. All right, now it is clear. So we are going to understand it where we can find the data points and what are our observables. Now let's get back to our, that how we can actually, what is dm, what is dh, and so on. So why I'm following this one, because again this is pretty much good paper to follow it. All right. And now over here, first of all, let us try to understand that what we are meant by dm, dh, and this. So dh is called as the Hubble distance and defined by c over here is the speed of light. All right. So dh is c over hz. Now you already know that when you are constructing any background model, you can easily compute hz by Friedman equation and so on. So 3h square is rho of total. So from there you can easily calculate what is this one. So you can just say that, okay, you can normalize it, and there is no requirement of normalization. You can simply say that c over hz, and I know what is my hz, and everything is fine. Right? So dh is now clear. What is dh? Now considering this dm, what is dm factor? This is angular diameter distance. All right. So because from here, if you are going to see, this is kind of angular diameter distance. And so what we are going to say about it, that dm is basically integral, you have 0 to z and dz over h of z. Now this has the certain form when we are considering that our universe is flat. Otherwise you can follow this equation number 15, where it has the form c over h0, and this is sk. Sk is a function of dcz over c h0. And what is this sk? Sk has certain form. sk could be sign of this function, and x is basically, this is your x, this whole quantity is x. So you can just simply replace x by this whole quantity, and you can say that, okay, I'm going to consider this hyperbolic type of universe, all right, where universe is basically open. If you are going to consider only omega k is equal to 0 corresponding to flat, then what you will realize is that you can just put everything over here. dcz over c has not, sk will be gone out, cc will be cancelled, hs cancel. So you will realize that this dm is basically nothing but dc. So dm would be dc of z. And what is how the dcz? Here is the line of sight co-moving distance. So line of sight means that when you are seeing it, this is called the line of sight, and this dcz is basically defined as c over h0 dh prime h0 over hz of prime, and then j0 to z. So I am basically not fan of this h0. I am just telling you that this is basically c integral and dz over hz. All right, so these are basically the thing that we have to follow. All right, so what are the quantities that we have evaluated right now? We have evaluated certain quantities. Let me just tell you what are the quantities that we have evaluated. So we have evaluated dc of z, which is basically 0 to z. Consider this is z prime and h of z prime, right? And similarly, I have dm of z, and in the flat universe, it is basically nothing but dc, right? And another one is that the Hubble distance dh is the speed of light over h of z. All right, so these are the things that we have, considering that I'm using the flat universe. All right. Now there is another quantity. If you have seen my Pantheon plus video, that where we are considering the supernova distance, I have this distance, luminosity distance, which is c plus 1 over z, 0 to z, dz over 1 plus z. Basically, it is nothing but 1 plus z into dc, or 1 plus z into dm, right? I have said earlier that I am not a very big fan of the integral. I am basically converting every possible integral into differential equations. Why I am converting everything in a differential equation? Because it is simple to use, and I have, I am not a very much fan of analytical solutions, as you can understand from my videos. And my research topic is basically, I am always playing with the scalar fields, and in scalar fields, hardly you are going to obtain any analytical solutions. So that's why I do not prefer to work on analytical solutions. All right, so the code that I am writing over here is not on the analytical solutions, although I am considering the LambdaCDM model. But I will show you that by following the same prescription, you can evaluate, you can just put your equations there. All right, and you can obtain everything in terms of numerical solutions. All right, so everything what I'm going to show over here to you is basically will be depending on the differential equations. All right, so now you are understanding this dl is equal to c of 1 over z and this one, and I can say directly that dl is equal to 1 plus z into dl. And if I know the evaluation of dl, then I can easily find out what is dm. Dm is just whatever the evaluation that I have already found out for dl, and then there is 1 plus z. Just divide this 1 plus z, right? And you are good to go, find your dm. All right, so this is the basic prescription. Now the thing is that I had already shown you that how you can convert this dl, all right, in my previous video, that I can just take d of dl over dz, and I'm going to use the chain rule to just do this equation, deal with this equation. So c into 1 plus z is nothing but z, and 0 to z dz over 1 dz over h of z, right? And then c of 1 plus z, and if I'm just taking the integral and derivative will cancel each other, and therefore I have h of z, and I know how I can write this everything in terms of dl. I can just say that because dl is this one, so c and this integral will be dl over 1 plus z, right? So this would be dl plus 1 plus z, c into 1 plus z, and h of z, right? D of dl dz. So this is the differential form of dl, all right? So now once I got the differential form, when I will evaluate, when I know what is the evaluation of dl, I can certainly obtain my dm just by dividing with 1 plus z, and you are basically good to go. All right. So this is the simple prescription that I'm going to follow, because I like speed and I don't want to compromise with speed. So that is my basic trick to actually gaining a lot of speed. All right. It is not just simple speed, but a lot of speed. Now, thirdly is a very simple thing that is I'm going to do. Let us just first tell you what is LambdaCDM, but before I have to explain what is basically dV or by RT, right? All right, let's get back to our again same analysis, because sometimes I forget. Yeah, over here you can see that in BAO measurements were also historically summarized by single quantity representing the spherically average distance. So this is basically called spherically average distance, and which is containing as z dm square of z and dh to the power 1 by cube. So if, let me just go back to my screen. So dv, if I'm correct, dm, then you have to square it whatever that you're going to get the value, and therefore dh to the power 4 cube. If I'm just summarizing it, or if I'm just opening the bracket, therefore this would be co by hz to the power 1 by 3. So these things that you have to program, right? Now you understand that if I know what is the evaluation of this dl, from this evaluation I can easily calculate my dm, right? And once I know the dm, I do have also again the differential equation for hz. So I know easily what is hz, I know what is my dl evaluation. From this dl evaluation I can easily calculate dm, and from this calculation I know what are the rate z. C is already known. I will just square it and I can easily calculate this dv spherically average quantity, right? Pretty much simple, right? So this is basically the basic recipe to working with the BAO data, right? All right. Now, when you understand these things, so first of all, how my code basically look like. So if I consider LambdaCDM model, you understand that these are the basic quantities that you're requiring. Rho m plus pm is equal to 0, and consider that rho d plus 3h rho d plus pd. In LambdaCDM model, pd is equal to minus rho d, so this will vanish out. But for now, I'm not going to vanish this, because you can have many models. Let us say you can have WCDM models. Maybe there are different parameterization. Let us say w plus v into 1 minus a, or let us say 1 by 1 plus z, and so on. Whatever kind of model you can have, right? So first of all, I'm basically telling you that I'm not a big fan of integrals, all right? I am basically fan of differential equations. And thirdly is that I don't like to compromise with speed, right? So keeping this in mind, and also I am very fond of very fond of dynamical system analysis. So if you don't understand anything about dynamic system analysis, you can see my other videos where you can find out how we can construct the dynamical system for pretty much any kind of differential, any kind of model, cosmological model, or any kind of nonlinear models, and so on and so forth, right? So over here you can see that you have Friedman equation. There is another recipe over here. Kappa square is basically 1 over 8 pi g, the Planck mass. So this is basically, this kappa will be the Planck inverse mass, and you have rho m plus rho lambda, right? Now right now I am just considering that pd is equal to wd into rho d, and here I'm going to consider that pm is equal to 0 of rho m. So this is basically becoming 0 because it is from verified that dark matter is kind of pressureless. Right now we are going to assume this one, all right? So 3h square is equal to kappa square rho m plus rho lambda, and what you can basically do is the simple thing. is dividing everything by 3h square. This would become 3h square and rho lambda over 3h square with multiplying with kappa. And this is quantity I'm going to call as rho omega m and omega lambda 1, right? So one of the initial conditions that you could, one of the initial conditions as well as one of the important constraint from your system in the system you can see from here is the Friedman equation. All right, you can see that if I know the evaluation of omega lambda, I can easily find out what is the evaluation of omega m. All right, so in cosmology, the Friedman equation is too much important. If you want to, say that I have built up any kind of model and my model is valid throughout the evolution, or it is giving you the unique solution, you must respect the Hubble, the first Friedman equation. All right, so I can simply say that omega m is equal to 1 minus omega lambda, or I can say that, all right, I don't want to consider this omega m, I can simply say omega lambda is equal to 1 minus omega m. So you can have these two differential equations. I can say that no, I am just working with this particular differential equation. I can easily know what is the solution for other one. All right, initial condition. To select the initial condition, we always assume that z is equal to 0, because z is equal to 0 representing the present moment. So everything what we are observing at a present moment, and we are basically seeing at the past. There is no way we can know about what will happen in the future. All right, this is the constraint. So I can say, I can simply represent it using not this color, but basically I can simply say that, okay, this is basically omega m0, omega lambda 0, and okay, I want to vary my omega m0, and I will say that whatever I can easily find out omega lambda 0 just by varying omega m0. So in my code, I will vary omega m0 from 0 to 0.6, not minus but plus, because we know from different various results that the dark matter contribution is nearly about 0.3, right? And I will simply obtain the initial condition for omega lambda 0, right? As you understand how differential equations work. Now, in order to constrain the dynamical system equation, what you have to do, you can just find omega lambda prime. So d omega lambda over dt is equal to, what is omega lambda? Kappa square rho lambda by 3h square. Rho lambda is again not a constant quantity, because here we can have this conservation equation. When rho d plus pd is not equal to minus of rho d, then rho d is not exact constant, but it is varying, right? So over here I can say that kappa square rho lambda dot over 3h square minus 2 kappa square rho lambda over 3h cube, and there is h dot. This is pretty simple. All right, so now I can do this one, that okay, kappa square rho dot is equal to, you can see over here. So if you already know, you can skip this thing. I am just doing it for the sake of people who are very new to this omega d, and I will just write rho d over 3h square minus 2 kappa square rho whatever the d or lambda whatever you can write 3h square h dot over h, right? So now kappa square rho d over 3h square is basically omega d or omega lambda, whatever you can say. This is minus and then 3 and then h and 1 plus, I can write omega d minus kappa square rho d over 3h square is basically 2 omega lambda h dot over h, right? Now you have this second Friedman equation that you can get it by equating the spatial component of Einstein's field equation, which is basically tell you that 2h dot plus 3h square is equal to minus kappa square pm plus p lambda. This will be gone because we are assuming that we know that dark matter is pressureless, kind of data is hinting us, and p lambda would be what? Omega d. 2h dot over 3h square, I'm dividing everything by this one, minus kappa square p lambda, I can write over here rho lambda wd over 3h square, whatever you want to use. So 2h dot over 3h square is equal to Kappa square 3 square is equal to minus omega lambda omega d minus 1, right? If I'm just taking the minus outside, 1 plus omega lambda omega d. Now I got 2 h dot over 3h square, right? So I know what is my h dot 3h square. So I will again rewrite my whole equation as d omega lambda over dt is equal to minus 3 omega lambda h 1 plus omega d minus, all right, 2 has dot, I can just multiply 2, 3 and 3 over 2. It has to be some h square over here, so I have to multiply over this one. So what is I have got? Then if I am doing this one, am I not making any mistakes? So this would be 3 omega lambda h 2 s dot over 3h square would be minus minus plus, and I will get 1 plus omega lambda omega t, right? Now you can see over here there is a h additional arising over here. I want to make it everything dimensionless. Omega lambda, I will have s dt normalize with s dt minus 3 omega lambda 1 plus omega d plus 3 omega lambda. Okay, everything is correct over here. Yes, it looks so. Omega lambda omega d. Now h dt is what? You know, h is equal to a dot over a, right? So if I'm just multiplying with dt, then there is a dt. What I will get is that dA over dt into 1 by a, there is dt, cancel out. dA over a becomes log of a, right? Now you can just say that, okay, this omega lambda, what I want is following. I want to convert it everything in terms of z, right? This is basically, we want to convert it into redshift. So d log a is basically 1 by 1 plus z. It will be d of log of minus because it will be inverse 1 plus z, right? So d of log of z would be minus 1 by 1 plus z and dz, correct? So dth or s dt is equal to basically what happened, minus 1, so it's 1. So I will just write over here s dt because equal to minus 1 by 1 plus z into dz is equal to blah blah, and over here I can just write d omega by dz and just taking it this side, minus 1 by 1 plus z will be the factor for this whole guy over here. I know exactly what is my evaluation of d omega lambda by dz, right? But now you can consider that, okay, I have just only one equation. How the hell I'm going to get the another equation for h, right? Because h is important. Because why h is important? Because over here I require h. In dl evaluation I need h, and h in terms of z. So very good. I have this guy over here. So I know what exactly what is my h dot. My h dot is over here. So I can write over here that s dot by h square is equal to minus 3 by 2 into 1 plus omega lambda omega t. Am I right? Good. Now again I can do the following trick. dh over h dt is equal to just one h would be over here, blah blah. I exactly know what is h dt is basically minus 1 by 1 plus z dz, blah blah, and minus minus would be cancelled out. Therefore dh over dz is equal to 1 by, this is whole quantity is like this, I'm just taking this side, 1 plus z, and then h 3 by 2 1 plus omega d omega lambda, whatever you can say. So now I got this differential equation, equation number 2, equation number 1, right? And another equation is d of dl over dz is equal to dl over 1 plus z plus c over h of z, if I am not making any mistake, right? Where is this? Yeah, c of 1 plus z into z. Now you may ask that what is the initial condition for this one? Pretty simple. Put z is equal to 0 and you will know that dl is basically equal to 0. Why? Because what is the integral form? If you will see the integral form, is this guy over here. Where is this DL, right? So when Z is equal to 0, there is nothing. DL plus something has to be constant, right? DL minus 0 has to be there, right? So when DZ is equal to 0, because it says that the interval Z is equal to 0 to 0, it's going to be vanish away, right? So you will have this DL is going to be only 0. So 0 to 0, DL is nothing, right? So the initial condition for DL is equal to 0. Initial condition for H0 would be only H0, right? So now what is your initial condition? I am going to get the constraint on H0 by assuming that, okay, I have to, because I have the differential equation and I have to put my H0. So I am going to consider that my H at Z is equal to 0 would be H0, and H0 is now my model parameter. So by varying the H0, I will obtain this DL. Now, initial condition for DL is always going to be 0. So there is no variation. Everything is all right, right? Now, how we can find the omega lambda 0? Omega lambda 0 is basically omega m0. Now, what I'm going to vary? I'm going to vary omega 0. From where to where? 0 to, let us say, 0.6, right? So this is it. So whenever you try to work with any scalar field, just try to make a very good analysis of dynamic system stability. Why I'm a fan of dynamic system stability? Again, I'm telling you that because whatever the model you are constructing, at least at a background level, it must produce a stable solution. If it is not going to produce a stable solution, how can we say that your model is legitimate, right? Some models are not at background, could be not stable, right? But it may, produce some kind of physical solution. Or when you are doing the perturbations, some of the physical quantities, for example, sound speed, it should not diverge, or any other quantity which requires to be always positive, it must be positive, right? Otherwise, at quantum level, or you can say that it can lead to some instability which you don't want in your theory. All right, so that's why if I'm just constructing a dynamical system analysis for any kind of model, I can do the two works. For I can easily obtain the stability condition, and I also know that what would be the ranges of my parameters. Secondly, I exactly know that whatever the solution that I'm going to get is going to be stable or not. All right, so here it is. What are the equations? The equations corresponding to omega lambda. What are the initial conditions? Initial condition is there. What is my equations over here? I know what is DL. Once I know the DL, I can just say that dm is equal to DL over 1 plus Z. And how can I easily find out? dV is equal to Z dm square C over H of Z to the power 1 over 3. Everything is done. So now all the mathematical recipe is done. Now we are going to move towards my Python code. And now you understand one important thing, that I haven't considered anywhere omega d is equal to -1. So in this case, you can consider various form of omega d. You can say that omega d is equal to 1 plus exponential or something like that, whatever you want, right? And you can say that these are the parameterization. I don't want to consider any kind of model. I just consider that omega d can be different, or dark energy is not the same as constant. It should be varying. Any kind of model you can fit without doing anywhere any integral. Let me tell you that I'm going to publish this code in my GitHub, in my GitHub repository. You can just find it out. So first of all, I'm going to tell you that what I have done over here. So the data that I have obtained from SDSS, I'm going to label it as CMB. All right, CMB BAO. I'm just telling it. It has 8 points. Let us say that because these are very short file, therefore I don't want to I don't want to make any text file. I have made one particular file, and I can just call this file anytime with any model without even need to change anything at all, right? So this file you do not require to change at all. I'm just telling you where you require to change. Otherwise, every time you can use it, the file still stays same, right? So this is the Z effective. This is dm over dm drd, right? Dm over rd. This is this is the Z corresponding to dm over rd, because for not each data you can find out dm rd. You understand that there is some data points where dm rd is missing, so I'm just extracting those points where dm rd is there. There is dm data. Again, what are the sigma? what is the error, right? Over here you have d hash data, d hash again sigma, right? And you understand that whenever we are having this dm, equivalently we are having dh, right? And again, now we have dv dz. dv dz is for dv over rt and corresponding to whatever the redshift that it is there for this data set. And dv data, and you know, if you will look at this SDSS to 2019 paper 2014 revision, 2024 revision, you can find it out that for certain, you know, redshift 0.85, you will have certain data and there is plus error and there is minus error. So for this, you have to do is that you have to first do the chi-square for this guy over here, another chi-square, this one, and then you have to average it out, right? So chi-square plus for chi-square minus, and then you have to do the half. This is the best way to, you know, incorporate the asymmetrical error. All right. So this is data point is pretty much clear, right? Let's move on to another section. So if I come over here, what I can realize is that first of all, I'm going to make a definition for CMB BAO, SDSS BAO. And there is again a free parameter. I told you that RD is my free parameter. So here I am just importing DL. I told you that this is depending on your DL solution, because from DL I can easily calculate my DM just by doing DM is equal to DL by 1 plus Z. So I have already computed my DL. I will import the solution of DL over here, right? I will also import the solution of HZ, H solution over here, and I will say that, okay, because I am treating RD parameter, I am not doing any differential equation over here. One of my parameter is basically RD because I require RD. Why? Because these things are really RD. So if I am saying the DM over RD, then automatically DM over RD will become this one, right? Both the side have to be equal. So R is going to be a free parameter. So if it is, sometimes it will be 100, then it has to be go there 100, and then it will do the chi-square analysis. So you understand this point, right? Over here, I'm just, you know, making an object that DMR DVL, whatever the value it will contain. First, that is the length. Length would be, you know, what is the length of DMR DVL? Because DM over RT, it has certain redshift, and that would be the length. So I'm first defining this length. Then I am going to calculate that, okay, whatever the DL value I have calculated, I had the redshift for this DM value. Calculate the DL only for that redshift, right? And there is RD, and since I am calculating basically DM, therefore there is have been 1 plus Z. And which Z I am talking about? The Z is corresponding to this one. I cannot just take any arbitrary Z. It's not arbitrary Z, right? So this is done. DM is done. In line 17, your DM and DR calculated. Now what else? I have DH over DR. Now again, simple. It is basically C over, this is the speed of light, RD has to be there, and H value at those redshift. This is done, right? And now I am coming to dV over RD. It has formula Z times. So Z is what? Z is for some specific redshift, right? There are two data point, 2Z. Now they are basically an array. First of all, it will take 1, and then it will be 2. So it will having some kind of list, if you understand some Python. Now DM for dV is square. Which one? DM for dV is square. Now again, you can see that DM for dV. Again, I have, you know, I require DM. I told you that dV over RD is basically what? Z into DM square. One DM I have calculated at different redshift, but again I have to calculate for this particular redshift where dV is valid, right? And there are only 2 data points. So I have also defined over here DM for dV, DL VL, and 1 by Z, which specific Z. So it will simply contain this dV Z, right? So dV Z has 2 data points, 2 redshift. It will simply calculate my DM for those 2 one. Now there is C and H for specific dVz, right? So this is computed, and then there is a power. This is power and RT. Everything is done. As I told you, how this chi-square will be computed. The chi-square will be computed like this. Where is chi-square? Yeah. So now, first of all, I have to find the residual. Residual means what? The model minus data. First, you have to do this one for chi-square analysis, and then you have to sigma I for each data set, right? Model minus data, because it was going to be a squared, so no problem. So residual is that dHr/dVl, whatever we have calculated the value, and there is a data point, and then I'm going to square it. I know, and again you have to minus half, because the likelihood you are calculating half chi-square, right? This is my chi-square, this is my half, and this is done. So this is for chi ds dRd. This is for chi dm dRd. So dm over rd, chi-square is calculated, and over here dv over rd, right? Once I have calculated the chi-square, I'm going to add for these three ones. All right. Similarly, I can do it for the bao DESI result. So here I'm just saying that DSZ, all the 8 data points. Why it is required? It is required for calculating AIC and BIC values. dm over rd for specific z, dm rd data points, dm rd sigma, ds rd data, because they are both sharing the same z, I don't try to repeat it, sigma, and therefore dv over rd, 2 data points, and here you are not going to find any asymmetric thing, so no asymmetry at all, right? So no asymmetry at all. Over here it is now finished. 2 data points. Now I am defining a function DESI BAO. Again it will incorporate the DL, hash value, parameters. You must understand that which parameter that you are basically obtaining. So the thing is that I told you, you have to be cautious over here whenever you are obtaining this RD. But again, I have made this file in such a way that you have to you don't be blind, first of all, because I am making this video to teach you, right? So I cannot just tell you that be blind. Understand it. When I will incorporate this file, I will make my parameter in such a way that it will only import the value where RD will be defined. All right. So you don't have to, in some way, you don't have to worry about anything. So now you understand that this RD is basically, you have to understand that where and what will be the position of RD. All right. I will come to this point later on. And now again, the same thing I have done it. No another thing defined similar way. So over here, you have to understand these things, that which redshift you have to use and so on, because it could be tricky. You may use the same thing, same different redshift for different different observable. So you should you have to understand that what is the difference in the observables. All right. And over here I have computed the necessary thing, chi-square for dmrd, chi-square for dhrd, and chi-square for this one. And what I have done over here is that chi total is chi dm over rd, dv over rd, ds over rd. And over here you can just I have already defined in terms of block. I'm going to call these things, all right, and it will simply giving me the chi total. So afterwards, you don't have to multiply additionally with -1/2 and nothing else. You have to just import the file. I'm going to tell you that how we can import it, because again, it will be the very important thing. Now my main file is this one. The main file will contain some equations, right? You already know that what are my observables. So first of all, this is my preamble. This is consisting of important modules. For an example, interpret 1, because whenever I will have the solution of Hz, I'm going to interpolate, because although I have some evolution of Hz, let us say that it will increase Hc, I know for some specific Z, right? So this would be if I'm using very small steps, lot of data points would be, but I require some specific Z, right? Z point 0.1, 0.2, 0.5, 0.7. So this interpolation will work. All right. Interpolation will exactly tell you that for which Z there is exact H. all right? And if I want to, just any data of h at this point, it will simply give me by using this interpolation method. So you may have already, studied in your BSc level that how the interpolation works. So this is Newtonian interpolation. Now solve IVP for this for the differential equation differential solver, and then there is an inverse of the covariance matrix and so on. And now I have saved this bao file as bao.py. So if when you are going to let us say that I am working with LambdaCDM new bao, this is my parent folder, you have to keep bao file in that folder only, all right? So bao.py, so I'm importing my bao from there. So import bao, I'm not going to write py, only I'm going to write import.bao, right? Because I'm using some functions which I have already defined over there, right? So if you really want to understand how these things work, you can see my other video, all right? I'm importing over here datasets. Datasets is in my different folder. That's why I'm defining it over here. I am also working with Pantheon datasets. In Pantheon datasets, there is a covariance matrix which is a square matrix 170171. So I have to reshape it, because if you will see their files, it is maybe nearly about 40 MB, and they will give you simply just the column matrix. So you have to reshape 1701 1701, and then you have to inverse it by using la.inverse. So once inverse is done, it is done. I told you that I can use any terms of parameterization. Therefore my first block would be that, okay, what would be your omega d? Omega d could be anything. Let's say that I am working with LambdaCDM first, the very simplest case. Z parameters EOS is equal to -1, return my EOS, right? So whenever you will encounter with omega d, you have to write this omega d, this is redshift, as well as this params. So params should be only params, all right? You don't have to do anything. So params is corresponding towards parameters. Now this is my parent equation. That what are my equations? So first of all, my equations is that what are my variable? First of all, my variable is omega lambda, second is h, and third one is dl. Now what are my initial condition? Initial condition is my omega m0 and as h0. Now because parameters will always contain in terms of a list, first position is 0th one, second one is 1, and third one is 2. So the numbering will go from here to here. So my initial condition corresponds to OD0. So OD0, I told you that I will vary OM0. This has to be OM0 over here. There is a H0 over here, and RD, because I'm making it a free parameter, so RD has to be also written here. So RD would be, whenever I will call RD, I will write params of 2, right? This would be RD. Now since there is no requirement of RD anywhere, just like just a calculate whenever we are going to calculate DM over RD, right? Right now I am just finding the evaluation. EQD, EQS, everything is gone over here. I am just writing over -1. So whenever I just have written -1, you can just write over here omega d, z, and params. You can see over here that whatever the params I have written over here, you have to just write this params over here, right? You don't have to do anything, because it will go this side, and if your EOS is different from -1, it will automatically take it that, okay, fine, something is there, right? You don't have to do nothing. Or if you don't know what is basically I'm meaning, you can see my other video. You can exactly know what is basically I'm implying. Now over here you have equidual, I have everything, and now you have to understand the order is important right now. So you can say that first I am calculate equidual, EQH, and EQDL, right? EQD for omega d, H, and this is for DL, right? Now this is important. Why? You have to focus it. Why this is important? Now this is again I'm going to talk about the ODE solver. So I am making a block ODE solution. It will just incorporate parameters. First omega m0, h0, and I don't require RD, but over here I'm just importing that, okay, RD is equal to params of 2, right? So the position is fixed. OD0 is equal to 1 minus omega m0. Omega m0 will be, coming from here to here, all right? OD0 will be given over here. Tmax is that how many points I'm calculating at each redshift. Solve IBPB, lambda t, y, y is for, these variables, right? Equation has some t, because redshift is basically what is this t, right? I don't want to, this is a variable. Y is your variable. First variable is OD0, sorry, omega lambda. Another value is h, and then there is dl. So you must understand this guy over here. If you are writing this one, the y will first understand that this is corresponding to this variable, this corresponding to this variable, this is for this one, right? So do not mess it. From where to where you want to calculate. So this is your initial and final. And now again, the way you have defined, these are the initial conditions. OD0, H0, 0. So DL, the initial condition for DL is not going to change. H0, it will coming over here. So H0 is your model parameter. Now it is coming over here. So this is it. T-evaluate, it is important because where you want to calculate your differential equations in order to plot it, and then there is a tolerance level, and I'm going to use the method RK45 because it has nicer speed when you are working with a simple model. But if you have a very different scalar field models, then RK45 is not going to work. T solution is equal to solution.t, right? And I'm first of all, I'm importing whatever the time solution is, right? Time solution is the free parameter solution. So whatever the solution it is. S solution is corresponding to Y1 because you can see over here that I require S solution. I don't require OD0, whatever your dynamic dark energy kind of solution I don't want. So this is the first place, this is the 0th place, this is first place, this is second place. 1th and Y2. I want H value, interpolate T solution, whatever the T solution that I have obtained, S solution, kind linear. If there is nothing, then you can extrapolate it. Similar DL value, TL solution, DL solution, and then extrapolate. Now this is your basically containing every data points, right? Now something important. So I have now as observation data, I told you that for me, I have CC as observation data, right? This CC will contain 31 data points, Z, H, and there is sigma for this one. So this is for my model H value, and for a specific Z for which the observation is the observational points has been given. So as data as this one, H value is coming out from my model, and there is chi-Hubble square. Right, so I have now everything and calculating it. Okay. Now I am not using the sum, I am just using the matrix multiplication. I converted everything into a matrix. So that's all. Right, now once I am done with this one, I am going to again defining the chi-H. Now it is again a very efficient way I have done it. I am not defining other blocks outside my differential equation solver, but inside. Why? Because sometimes I don't require this chi solution. Sometimes let us say I want to constrain my model using simply Hubble data, right? So I don't require it. So if you are not going to define over here that I want to explicitly compute it, it will not go inside it, right? Because again each time if you will compute chi-SN and you are not using it, you are basically investing a lot of your computation. So I don't want to do it, right? I already explained you how you can do it. So mu VL SN, so this is basically this like this one. Mu is equal to what is this? 5 log 10 DL plus 25, right? If I am just using Pantheon plus whose calibrated data, I am not using the MB for the absolute magnitude of supernova data, right? So if I'm just using this one, this formula over here, what I have done over is that I am just importing this one 5 log 10 from the numpy file, DL value, and there is a redshift. Redshift it was I have already obtained the redshift from the Pantheon file, Pantheon dataset. So I'm just taking this block redshift. And whenever I'm going to use it, I'm just will say that, okay, whenever I have redshift is equal to Z data corresponding to supernova or Pantheon plus. And then it will automatically come over here, compute it. Residue, and then I have the covariance matrix already defined over there, inverse covariance matrix for this guy, and then transpose this 1701 into 1701, and then this residue. And then simply give me the result or residue, this is whatever the chi-square, this is my chi-square, right? So this is also computed. Now come to the important part, the BAO result. So how we can do the BAO result? BAO computation is again pretty simple. I have imported BAO. Import BAO. BAO contains what? BAO contains two files. BAO contains two definitions, right? One definition is for DESI BAO, right? And another definition is we having CMB BAO. So first of all, I am going to do the calculation for SDSS CMB BAO. First block is for DL well, because I'm importing the capital luminosity distance DL, right? So over here, it will go to DL well, right? Because there is a list of data points, H value I require, and now I require a specific RD. So what I am done is that, okay, parameter is some kind of object. It will just import the second value of my whole parameter, because in my parameter I am defining that RD should be 2. So now my BAO file does not require any kind of modifications, right? If maybe you are defining parameter in such a way that first one is not RD, second one is not RD, third one is not RD, fourth one, so it will be 0, 1, 2, 3. So it will be params of 3, right? That's all. And similarly, I am just importing this one. Chi total would be chi Hubble, chi bao DESI, chi bao CMB plus chi SN, right? I have also incorporated DESI result. This is supernova. So if you understand this one, so I don't think so that I require to give you this one. So what I will give, right? So how I can just compute SN also? I will write over here chi SN, and then this will be DL well, right? So DL well is equal to DL well, okay, value. You can just compute it, and redshift is equal to what I have imported this jet data SN, that is from observations. That's all. So chi total would be there. Chi total is done. And now over here I am defining another important block, that all right, there is a log probability, parameters would be there. If there is a result, when everything is computed, OD is basically returning your chi total, right? So this is what you're returning. You're returning is chi total. So result RES is equal, result is equal to OD of solution, done everything, and then imported result, right? And if NP dot this one, if somehow calculation is not done and somehow it is containing NP infinite solution, then it will say the Emcee that okay, this solution is not valid, make the likelihood very, very, very lower. It means that you can discard the calculation and you can further go on. All right, and then return the result. Result, when it is infinity, it will, this block will result minus infinity. If there is a result, it will simply give you the result. Return is result. Now this block is also done. But now where is my Emcee? Emcee will come over here. The most important part is, because this is the equation part is done, differential equation is done, BAO part is also done. Now who is basically driving it? The engine is done, but now I have to set up my driver. My driver is being set up by over here, imported everything. See over here again, also I am to import BAO, because I want to calculate my AIC, BIC, and so on and so forth. Therefore, that's why I want to know what will be the length of the data set. So first of all, I am going to import all the data sets, and I know that okay, how can I import my length of the CMB BAO data, SDSS data length, and DESI data length. So I told you that I have just import BAO, and from the BAO I have this whole Z data, right? So bao.cmb BAO of Z, it will just go to the length of this array. Consider over here length, and this is length. So if I want to see that okay, I'm using BAO DESI, BAO CMB, and CC data, right? Then length of this one, length of this one, and length of CC. So this is 31, this is 7, and this is 8. 31, 7, 38, 38 plus 8 is 46. So 46 data points I have, right? This is done. And what I have done is that I have to use, I want to save my file. So I am first describing what is my file. File name is LambdaCDM plus bao level figure cc plus bao. Defining my AIC and BIC, again where this n comes for the BIC calculation and so forth. And there is n dimension, that how many model parameters that you are fitting. I am fitting basically 3 model parameters. One is OM0, H0, and RD. Basically it is 3. How many live points? This is not required for here. This is for different things. All right. Now I am defining that, all right, where I can, right now this is my driver, but how this driver is basically going to communicate with my this file, this equation file. So for here, I am just defining my new block, likelihood block, where I'm going to defining that, okay, import my these files. Now, what Emcee is basically doing is that you can generate anything. It will not see you that if you are saying that, okay, OMG, I require 0 to 0.6, but when Emcee will generate, it can generate any kind of value. It does not have any specific thing. It can just pick anything. I am telling the computer that, all right, if this guy is not generating any value which is in this range, then just make the likelihood go away. Just discard that point. Similarly, this guy and similarly this guy, RD has to be 100 to 300 because CMB also tells that RD is near about 147.7 megaparsec, right? This is the distance. So that's why I'm varying it 100 to 300. You can just vary it for 100 to 1000, 2000, no matter what. But it will again come back to this one because again, I told you, I explained you in my previous video that basically what is the meaning of data analysis. You can see that video if you don't know. And now my result, compute this log probability of parameters that I have already made over here in the new LambdaCDM, right? I am just using this log probability and it contains only params, but with new LCDM, because new LCDM is containing this one. So new LCDM dot log of params. Everything it will generate these parameters over here and it will compute the result from here, right? And this is the result that is basically read by the Emcee, right? And now it will come over here. I have defined various things. You don't have to, I just defined that what is my CPU, at which time I have started, what is my file name. You can say that, that I'm not writing everything every time. Just say that, okay, F, write my file name and what is the total number of analysis, because, I do a lot of analysis. So I keep on forgetting that which thing I am doing, and that's why I'm using these locations to basically understand that, okay, fine, what is basically I'm doing, right? N workers is important in Emcee, n dimension and n iteration is 20,000, and now I am uniformly my Emcee, I am uniformly making my Emcee has two things, blue and red. There is a probability of producing all those things. You can see that low and high, because these are nothing, these are just like that, no use, right? The use is log over here, the constant that we have put over here. So I'm saying that 0 to 0.7, 40 to 100, 100 to 300, randomize our, randomize it, right? And with the pool 4, it is for the multi-processing technique. You may have different CPUs. In CPU, there are different threads, right? Let us say you have octa-core CPU. If you are using i5, maybe you have 4 CPUs, right? And a CPU has 8 threads. So 8 threads are basically computing it. In my computer there is 12. So 12 things will actually work at the same time. Understood? So Emcee, this is the same thing I told you in a previous videos. N worker, n dimension house, and there is a likelihood, and there will be pool is equal to pool, and there is live dangerously. Then do not care, just do everything. Whatever the wall you will encounter, completely forget about those things, and then simply run. There is an initial, there is an iteration, and then whatever the progress that is there, I want to see it. I want to see the progression, right? And then discard it. Discard is important because whatever the change that you are going to get, you are not going to get all the change. You have to, sometimes you discard it, because discarding is important. Why it is important? Because let us say that your system is, picking some good value and it is not basically randomizing it, right? Randomize. I want randomized value. I don't want that my results should be somehow polluted by my previously thought answer, right? So that's why this card is important. Thinning it at whatever the result I am going to get, let us say 20,000, 10% should be thin. 10% should be removed from it. And now I'm going to get sampler.getChain and all these things, and there is name and all this over here. First of all, you have to write the name. What are the parameters that you are working with it, and then the labeling, because I am going to you can see that various way you have this triangular type of plot. So this is basically give you the print for latex type of printing. sample to for Emcee samples, because I'm incorporating Getdist for this plotting, sample chains, whatever the name and labeling that I'm going to use over here. So chain is coming over here, and this one. Now I'm going to print it. Whatever the print is, that here is the result for this one. Again, I will forget if I'm not printing it. And I'm going to say that whatever change that I have got, has it converged? And it will always give you the value of 1.001. If I am having a 3, so I will just say that not 1.001. If you will get 1.01, then your chain is now converged. You will not going to get any different result if you are going to, compute it for 1 lakh, 2 lakh or 3 lakh iterations. It is wastage of time, wastage of computer hours, right? So you have to understand. So this is called Kalman-Rubin statistic, which is important. If you are reporting anywhere in the journal, you must first of all compute this Kalman-Rubin statistic. You don't have to do anything. You just have to, that from Emcee sampler variation name, wherever you have already defined the name, you just do this one, and it will just simply tell you that, okay, your chain has now converged. All right, you are not going to get different result if you are going to run for large time. Log probability, I'm going to get this one, that what is the log maximum log probability. It will having always giving you that in the positive sense, the result positive or negative. Yeah, it is having the minus result. So minus in the list, whoever is the least one will be the maximum log likelihood, because it is in minus. And then you can have from here, you can say that, okay, in the index file, what are the maximum of those parameters? Again, I can just print my chi-value square. I can just also print the reduced chi-square. Reduced chi-square is very much important, because this chi-square reduce will give you that whatever the chi-square, and then whatever the data you have used minus n dimension, right? N dimension is that how many model parameters you have. If you will do it, it is assumed that if it is lesser than 1, then you are overfitting it. Means that somehow you are making some mistake. You should not report this one. But I am telling you that if you are going to use this Hubble data or maybe BAO data, this is going to come out like minus 0.9. So for lesser data sets, it is basically going to get lesser than 1. So do not do. But if you are working with a very large data set, let us say Python data, you must have this chi reduce 1.002 or something like that. You should not be report 2 or 3. It means that your model is not fitting. But if you are gaining the result 1.04, 1.02, 1.0, something like nearly about 1, it means that it is very, very fine. The model is basically doing absolute fine result, right? And again, you can just compute my AC value, and I have also taken that, okay, fine, I'm making a stat file over. You can see over here a stat file, and in a stat file I am going to get this kind of thing, that okay, I have computed for LambdaCDM BAO result. AIC would be this one, BIC would be this one, likelihood is minus 19.70, minimum chi-square is 39, reduced chi-square is 0.895. As I told you that it will keep on happening if you are going to get the lowest data set. And this is the parameters. Maximum likelihood would be like this, omega m0, omega this one, and so on and so forth, right? Okay, yeah, so file write, by using this file write, I am just making sure that everywhere these things are already saving it. And now I am plotting the triangular plot sample m2 level. Now again, I am not writing everything. So this is F command, and level fig will ensure me that okay, whatever the given labeling I have done it will automatically come over here. And simply I'm saving it by using F file figure and whatever the file name, so that it will little bit automatic. I don't have to go everywhere each time. Okay, I have to remove this one, because I have seen so many time that it is very, very inefficient way to do something, right? And now everything is done, and I'm also losing my whole lot of energy. And let's go to write our code. All right, so over here we have the code, and I don't want to calculate right now this SN. So ODE solution. All right, I don't want to calculate U right now, because it will take a little bit more time. All right, so what I'm going to basically calculate is the following. Exit, I must ensure first of all that what is the result that I'm going to get. Execution file. In execution file, I have to see that my n is fine. Okay, CC data, DS bao, CMB bao, file name is good, bao+cc, labeling is fine, CC plus BAO data, good. And I'm going to use Python 3, LambdaCDM, whatever the execution file I have. I'm going to hit the computer and boom, it will start. And you can see that is the result. That is the iteration that you are going to get 68, 64, 65, 67. And this is computing for 1, 2, 3, 20,000. So you have to wait for 4 minutes and 5 minutes. But I'm not going to wait it. I'm going to simply show you the result, and the result that you will get kind of something. Omega m is nearly about 0.30. H0 is nearly about 9.5, 1.8. And RD, the redshift, is 145.2 plus minus 3.6. So this is the way result you are going to get. So this is the triangular plot that you are going to get, right? And everything is good. Omega m, H0, and RD is fine. You can see very good contour over here. And this is the 68% result, 68% value at this distribution, right? This is called 1 sigma. Another 2 sigma is at 90%, and so on. So I'm not interested in 90%. I'm just interested in 68% distribution. Okay, 68% population, and this is the result that you are going to get with the free RD. So I hope that this video is basically adding you something, and if you are finding that it is important, also, yeah, I have heard, and many inquiries have been posted to me that please make a video on BAO and explain it, that how we can add some different data sets. You can see that in CC data there is no role of RD, but still I am gaining RD by using the chi-square for each and everything, just by adding it, right? So this is how you can incorporate different you can constrain different variables, different parameters using the different data sets. All right, so if you're finding this video very amazing and very helpful, kindly share it to the young researchers, share it to your MSc students, BSc students, also with yourself. You can learn a lot of things with this thing, and you can construct your model, implement it, and publish it. And make sure that whenever you are going to publish your result or publish your manuscript in a journal, make sure to also cite my paper or cite my video, maybe in form of a GitHub channel or GitHub repository. Just whenever you can mention it. You can also come here and comment it that okay, here is we have worked out with your this one. So that is the important thing. I'm showing you the code in this way that you don't have to be professional in Python, and yet you can in any way you can implement your model and put a constraint. You can see that how beautiful your model is, or what kind of constraint you can get in your model parameters, right? So this is too much important. When I was doing my research, there was no one who helped me. Somehow I got help, and I understood everything, and my job is to make it public, so that MSc student or BSc student or any young researcher or any old researcher can take advantage of these particular codes or this understanding of data analysis. So I hope this video adds some value to your research. Make sure to make sure to subscribe my channel and hit the like button. Thank you very much. This is Leonardo signing off.